Good morning. Okay, so last class we had discussed the property of the dimension of the subspaces, right? We had shown that the dimension of W1 plus W2 will be same as dimension of W1 plus the dimension of W2 if W1 intersection W2 is 0. And then if not 0, then we have shown the more general form of that. Dimension of W1 plus W2 will be same as dimension of W1 plus dimension of W2 minus dimension of W1 intersection W2. So those two results we have seen, and we have proved those two results using the concepts of basis and then basis, subspaces, and then as well as the dimension linearly independent. All these four concepts were used to derive these two results. Now we'll look some we'll look at some problems for basis linearly independent um, subspaces. Okay, let's look at some problems based on that. Okay, so let us look at some problems today. Okay, so let us have this vector. Show that the vectors. Let us take three vectors. Show that the vectors alpha 1 equal 1 0 minus 1, alpha 1 equal to 1 0 minus 1, alpha 2 is equal to, okay, 1 to 1, 1 to 1, alpha 3 is equal to, okay, 0 minus 3 2, okay, 0 minus 3 2, 1 0 minus 1, 1 to 1, 0 minus 3 2. Form a basis for R3. Form a basis for R3. Form a basis for R3. Express each of the standard basis. Express each of the standard basis vectors. Each of the standard basis vectors as a linear combination of as a linear combination of alpha 1, alpha 2, alpha 3. Okay, so there are three vectors are given to us. One is that alpha 1, alpha 2, alpha 3 is given to us. We have to first show that it is a basis. So basis means we have to show that two things. One is that it is a linearly independent, and the second is a spanning set. Okay, linearly independent, and then it is a spanning set. Let me write in the exercise whether it is correct. Okay, so what we are going to do that, so that of course the matrix approach we have not used to do well, but we may use those concepts here. Okay, if you want to show something vectors are linearly independent, it is sufficient to show that this alpha is are invertible. Okay, if it is an invertible matrix, then you can, you can say that it is linearly dependent. So that concept we can use here. So we have a solution be expressed as a linear combination of this vector, so that will form a basis. That is okay. So in other way, so we have already shown that way, linear independent in different way we have shown. Now we are going to use the matrix approach. Am I audible to everyone?
Yes, sir.
Yes, sir. Okay, fine. Okay, to show that the vectors are linearly independent, to show that the vectors are linearly independent, okay, linearly independent, it is sufficient to show that it is sufficient to show one can say that it is an okay, sufficient to show that this alpha 1, alpha 2, alpha 3, okay, should be written as a row, but it should be an invertible matrix. Then one can say that it is a linearly independent vector. So you can make use of this thing anywhere. expressed as the matrix A. Now we'll write this as a row. First row is alpha 1, second alpha 1, and then 1, 2, 1, and then 0, minus 3, 2. Now can you use row elementary operations to reduce this into as an invertible matrix? Can we use row elementary operation? Use row elementary operation. Use row elementary operation. Can you tell me the final matrix? What do you get? Can you just tell me the final matrix? What do you get? So can you make use of that? Just tell me the final matrix. This we can do another operations. Okay, so this one can be multiplied with minus 3, and then you can just do that. This is 1, 0, minus 1. We'll keep it as it is. So this can be divided by 2. So this can be written as 0, 1, and 1. So now this you just see that what operations we can do. Suppose you can uh, maybe you can do with this maybe the second row instead of third row, because if you subtract this again you will get some number here. So instead of the third row, so if you do it with the second row, so maybe you may get, because 0, this is 0, and then this is minus 3, 2, that is you will get minus 1, and then 2 plus 2 will get 4. That will once again that will give us something different. So maybe otherwise what you do, that you multiply this with 3 and this with 2, so that this will be 0. Okay, and then here you will get 5. This is another operations you can do. So the 5 can be replaced by 1, because you can divide by always by 5 by 1 by 5, right? So now this can be further expressed as 1, 0, minus 1. Okay, 0, 1, 1, and then 0, 0, 1. Now what are the other possibilities we can do? Okay, so what we can do, that we can add R1 can be further reduced as, okay, you can add the first and third row. So that is 1, 0, 0. So 0, 1, 0. So 0, 0, 1. Finally, you will get. Okay. And then this will be subtracted with this also. So you are going to get this one, 1, 0, 0, 0, 1, 0, 0, 0, 1. So this says that you can able to find out an invertible matrix. So this will be linear independent vectors. Okay, this clearly shows that, because you see that these vectors are each and every column you have 1 0 0 0 1 0 0 0 1. Or if you take this as a first vector and this is second vector, this is three vector. This is alpha 1 is 1 0 0, alpha 2 is 0 1 0, alpha 3 is 0 0 1. Obviously, this is a standard basis. This will be linear independent vectors. Now, what do we have to write that? Now we have to write these standard basis. This is a 1 0 0 0 1 0 0 0 1 as standard basis. Now from this we can say alpha 1 we are getting okay. So instead of alpha 1, because alpha 1 we have already given. So therefore we can say that 1 0 0 and then 0 1 0 and then 0 0 1 are the standard basis. Or the standard basis. So independent analysis is done, and then it will be form a basis also, because it reduces to 1 0 0 0 1 0 0 0 1. So now the second question we have to choose. So therefore this will form a basis. Alpha 1 and alpha 2, alpha 3. Alpha 1, alpha 2, alpha 3 form a basis. Alpha 1, alpha 2, alpha 3 form a basis for R3. Okay. Some of the problem I did it a different way, but this is a different way. So you can go for any approach. Now we'll go to the second question. What was the second question? Express each of the standard basis, okay, standard basis vectors as a linear combination of alpha 1, alpha 2, alpha 3. Now we have got already standard basis vector. Okay. Now what we have to do, that we have to express this standard basis vectors as a linear combination of this vector. What is the meaning of that? The second question. Express each of these standard basis vectors. That means what? We have to show that we have to show that 1 0 0 is same as linear combination of that. Let's say C1 alpha 1 plus C2 alpha 2 plus C3 alpha 3, something like that. This is a linear combination of that. And similarly 0 1 0 0 1 0 should be expressed as some D1 alpha 1 plus D2 alpha 2 plus D3 alpha 3. Similarly 0 0 1 should be expressed as, let's say that E1 alpha 1, E1 we use for this one, let us say some B1 alpha 1 plus B2 alpha 2 plus B3 alpha 3. This is what we have to show. So each of these standard basis vector 1 0 0 0 1 0 should be expressed as linear combination of the vectors alpha 1, alpha 2, alpha 3. That is the question. That is the question we have been asked. Okay, that's what we have to prove it. Am I audible to everyone? Hello?
Yes, sir.
Yes, sir. Okay, great. Okay, so now in order to show that each of these standard basis vectors should be expressed as a linear combination of that vector, again we are going to find out some matrix. Okay, some matrix approach only. So because I want to write alpha 1 and alpha 2, alpha 3, first I will consider alpha 1. Alpha 1 is what? 1 0 minus 1. Alpha 2 is once again same, that is 1 2 1. Now alpha 3 is same, that is 0 minus 3 2. Now what I want to write, each of the standard basis should be expressed as linear combination of this vector. So I should consider standard basis here 1 0 0 0 1 0 0 0 1. This is the standard basis. Now what I want to use that, now I have to again use the row elementary operations to see that, to find something is some, okay, now this will also change and this will also change in order to get in order to get some matrix P, that will be an invertible matrix. So based on that, okay, so now this will reduces to 1 0 0 0 1 0 0 0 1, and here you will get some different matrix. Okay, that is nothing but the inverse of this matrix, which will give us the linear combination of these vectors. Okay, so that is the other way of, short way of doing it. So we already know that this will reduce to this. This will reduce. We already know that this matrix 1 0 minus 1 1 2 1 0 minus 3 2 reduces to this only 1 0 0 0 1 0 0 0 1. That is what we have already written here. This will reduce to this matrix only. But But we have considered this also 1 0 0 0. So whenever you do some operation here, so here also you'll make the operations. Okay, here also you will do the same operations. So if you use that row elementary operation, so you can just verify that using row elementary operations. Using row elementary operations, okay, we have, I'm just writing the final matrix. From this you have 1 0 0 0 1 0 0 0 1 you will get, but this will also change because you are subtracting with this minus this and this minus this, all these operations you are doing. So now this will be also changed. So what I got is, so we will be getting this matrix 7 by 10, and this is 3 by 10, and this is 1 by 5, and this is minus 1 by 5, and this is 1 by 5, this is minus 1 by 5, and this is minus 3 by 10, and this is 3 by 10, and this is 1 by 5. So you make sure that this should be an identity matrix. Till that you have to do this operation. Okay, till that you have to do this operation. So this matrix should reduces to 1 0 0 1 0 0 0 1. So don't ask me, sir, again you will subtract these two and all. If you subtract these two and all, then you won't get an invertible matrix. In order to get an invertible matrix, so this matrix should reduce to 1 0 0 0 1 0 0 0 1. Because what I know from that, so the invertible matrix means was P into the matrix A equal to I, or you can say that A equal to P inverse. It should be A equal to P inverse. Okay, so if you want to get this, so this should be a matrix P. If I want to multiply this with A, then I should get an identity matrix. That is the approach we are doing it here. So now this one will give us, okay. Now this is nothing but we have considered 1 0 0 0 1 0 0 0 1 in place of that. Now this will give us the constant value C1, and this will give us the constant value C2, and this will give us the constant value C3. You don't need to find out something. This is an idea. So similarly, this will give D1, D2, D3. This will give A1, B1, B2, B3. That's it. We are done. Now you can verify directly that this is nothing but 7 by 10 times of alpha 1 plus 3 by 10 times alpha 2 plus 1 by 5 times alpha 3, which is same as 1 0 0. Let me write that, then we will check at least one equation. And from the second equation, it should be minus 1 by 5 times alpha 1 plus 1 by 5 times alpha 2 minus 1 by 5 times alpha 3, which is same as 0 comma 1 comma 0. And the third thing, minus 3 by 10 alpha 1 plus 3 by 10 alpha 2 plus 1 by 5 alpha 3 is same as 0 comma 0 comma 1. So you can easily verify that whether these equations are true or not, right? Because alpha 1, alpha 2, alpha 3 are given to you. You substitute here alpha 1. Let us say the first equation. So let's say, suppose, let us verify that whether that is true or not. 7 by 10 into alpha 1. What is alpha 1? What is alpha 1? You go minus 1 here. Plus 3 by 10 times alpha 2. Alpha 2 you got 1 2 comma 1 plus 1 by 5 times alpha 3. Alpha 3 is what? 0 comma minus 3 comma 2. Now I should get this 1 comma 1 comma. So this is 7 by 10, 3 by 10, this is 0. So 10 by 10, then I will get 1 here. This is 0, this is 3 into 2, 6 by 10. Okay, this is minus 3 by 5. Okay, so that is nothing but, once again, this is 0. So this is minus 7 by 10, this is 3 by 10. Okay, 3 by 10, this is 2 by 5. So that will give us, you'll get 0. So you'll get 1 0 0. Okay, 1 0 0. Similarly, for second equation, if you consider 0 1 0, and the given vectors is a linear combination of the vectors for 1 0 0. Okay, so now this problem we have done. So this problem, one problem concerning to the basis we have done. So if you want to show it is a basis, now you just see that whether so if you reduce this like this 1 0 0 0 1 0 0 0 0, you don't need to show for this one spanning set also, because 1 0 0 0 1 0 0 0 are standard basis only. So you don't need to go for spanning and all. So directly you can say it forms a basis. And in order to express that as a linear combination of that, then you need to find out something like this, some invertible matrix, in such a way that this should be expressed as linear combination of the vectors. Excuse me. Okay, let us look at this problem. And let V be the space of all matrices. Let V be the space of all matrices. Space of all matrices over F. Okay. Let V be the space of all matrices over F. Find a basis. Find a basis. This is given A1, A2, A3, A4. Find a basis for V. Find a basis for V such that AI square is equal to AI for each I. See, let V be the space of all matrices over F, and find a basis A1, A2, A3, A4 for V such that AI square is equal to AI. Okay, so that means it is something like that. Whatever matrix you consider, square of that will be same as that matrix. Okay, so you need to consider like that. So you need to consider four matrices A1, A2, A3, A4, and then you have to verify that that is a basis. So basis means you just see that it is linear independent and it forms a basis. That's it. Okay, can you construct any example like that? Can you just give me an example where you can do that? Can somebody give some counter examples which will satisfy this condition? AI square is equal to AI. Hmm. Hello. Okay, so we have to satisfy this condition. So ai square equaled ai square is equaled ai for each I. That's what you have to show. So you consider two, three, the four vectors. So that should satisfy a1 square equal to a1, and then a2 square is equal to a2, and then a3 square equal to a3, and then a4 square is equal to a4. This should satisfy. Okay, a1 square equal to a1, a2 square equal to a2, etc. Okay, now if I take the matrix like this, just tell me whether these are the correct matrices. Okay, suppose I matrix A1 as I am choosing as 1 0 0 1. So you can just see that A1 square is what? A1 square is what? 1 0 0 1, and then 1 0 0 1. So this is same as 1 into 1 0. So this is 1, and then 0, and this is 0. So this is 0, this is 0. This is 0, this is 1. So that is true. And similarly, if I take a1, this is a1, this is a2. If I take like that, let's say anything you can take, whatever combination you can take. So this is 0 comma, you don't need to take 1 also, that whatever, that is your choice. So this is once again that all these entries will be 0. If I multiply with only 1, then I'll get this a2 square is also a2 I'll get. That's not an issue. Now we'll have a3 like this. Okay, suppose I take a3 is equal to, suppose I take a3 equal to 1 1 and then 0 0, something like that. So what would be the a3 square? So I will get 1 1 here. Suppose, let us see that. So a3 square would be, okay, 1 1 0 0 and then 1 1 0 0. So I'll just multiply, this is 1 and then 0. So I'll get 1, and then if I do this one, this with this, and okay, so I'm getting that. Okay, so I'm getting, just because you have a only 1 year, so this will be 1 year. So that will multiply over here. You will give 1, and here also the rest of the entries are 0. That's the same thing only you will get. And similarly, A4 also you will get different things. Suppose we consider 0 0 1 1. So you will get that matrix. So all these four matrices will form. This will satisfy this condition. So therefore, you can write A1, A2, A3, A4 can be written as that. So now they'll will show the linear independent, because spanning set you can consider ABCD, that instead of that you can, whatever you want to consider, you can do that. Okay, we'll show the linear independent. Okay, linear independent, and one more thing is that it is a 2 by 2 matrix. A 2 by 2 matrix, the maximum dimension will be 4. Like, you can prove that. Okay, the dimension of that will be 4. So we'll show the linear independent first. So linear independent means what? Suppose you take A into A1, A into A1, okay, BA2 plus CA3 plus DA4, we equal to 0, we have to consider, right? And then we have to show that A equal to 0, B equal to 0, C equal to 0, and D equal to 0. It is already given in terms of the matrix form, so it is better that you write in terms of this only. A should be multiplied with the matrix given 1 0 0 1, and then B should be multiplied with 0 0 0 1, and C should be multiplied with 1 1 0 0, and then D should be multiplied with 0 0 1 1, and this is, we'll write as a matrix form 0 0 0 0 0. Am I audible?
Yes, sir.
Okay, great. Now you can add these things. So you have A and then 0 and then C and 0. So the first thing you will get A plus C, first entry. And second entry, this is 0 0, and this is C. So you'll get only C here. And then you'll get 0 0 0 D. So you'll get D here. You'll get here. So you will get A plus, okay, A plus B plus D, you are getting, right? Getting A plus B plus D you will get. So you'll get 0 0 0 0. From this observation straightly we are getting C equal to 0 and then D equal to 0. C and D are 0. C equal to 0 means what? A plus 0 equal to 0. So implies that A equal to 0. So A equal to 0, D equal to 0. Okay, so A plus B plus D. So from that observation, we can see that A plus B plus D equal to 0. So A equal to 0 and D equal to 0 implies that B equal to 0. So all these entries are zeros. Okay. So for A equal to 0, B equal to 0, C equal to 0, D equal to 0. So they form linearly independent vectors. Okay. And you can write this also true. If you take any matrix A, B, C, D, you just see that you take any entries you have to choose like that only. You have to choose A, B, C, D. It should be expressed as this is set of all 2 by 2 matrix. This will be expressed as linear combination of the vectors. Okay, you can just verify that. So therefore, a1, a2, a3, a1, a2, a3, a4 form a basis. I want to verify this thing. Okay, form a basis. Just verify that later. So this will form a basis. So this is how you have to construct an example. Okay, if something is asked like that. So Acha, can you try this problem? Okay, can you try this problem in terms of this row elementary operations only you can do. Okay, based on the row elementary operations we have done. So try this problem. Okay, suppose we are given, suppose use matrix approach only. Okay, suppose that alpha, beta, gamma be are three vectors which are linearly independent, which are linearly independent, which are linearly independent. Prove that alpha plus beta prove that alpha plus beta, beta plus gamma, alpha plus beta, beta plus gamma, gamma plus alpha are linearly independent. Okay, so just try this problem. Okay, I've done two problems based on that. You just try this problem. So one idea is given that you are given alpha, beta, gamma are linearly independent. Okay, alpha, beta, gamma are linearly independent means what? You have to there is a combination provided that constant values are zero. Okay, let's take a alpha plus b beta plus c gamma equal to zero means a equal to zero, b equal to zero, c equal to zero. That's what we know. And now if you want to show something is linearly independent, so you want to show alpha plus beta, beta plus gamma, gamma plus alpha is linearly independent, means you consider linear combination a into alpha plus beta plus b into beta plus gamma plus c into alpha plus gamma. Now you have to just consider that the coefficients are zero. Okay, what it will give us? Just then that will give a system of equations in ABC. Okay, that will give a system of equations in ABC. So either you find out the constant value is zero directly, or you go for a system of equations, and the final matrix should reduces to, okay, 1 0 0 0 1 0 0 0 1. If it is a unique solution, then you can have this a equal to 0, a equal to b equal to c equal to 0. Then you can say it is a linearly independent vectors. Can you try now? Just try. Just tell me that whether you get all these constant values are zero. Okay. Has anybody got the answer? Has anyone got the answer?
Yes, sir. Sir, we
Yeah.
can take P into alpha plus beta plus Q
Okay.
into beta plus gamma plus R into
Okay.
gamma plus alpha. Then
Okay.
we will rearrange it. It will become P plus R into alpha, P plus
Great.
Q into
Yes. Yes.
beta, and Q plus R into gamma.
Yes. Fine.
And then we can prove that P equal to Q equal to R equal to 0.
Yeah. Yeah. Correct. Correct. So you can either go for that directly. You can solve the system, or you can have a system of equations in terms of a P, Q, and R. And I think that will reduce us to your the system will give us the unique solution. If it is a unique solution, then the vectors are linearly dependent only. Yeah. That way we can do it. Yeah. Correct. That way you can do it. I think that final reduced matrix, if you get something like that 1 0 0 0 1 0 0 0 0 1, then from the back substitution it will be very clear that C equal to 0, B equal to 0, A equal to 0 only. That is the idea of getting in this matrix this standard basis 1 0 0 0 1 0 0 0 1. Why we are getting that? Why we want that final matrix should be like that? If you write 1 0 0 0 1 0, suppose if you want at the back from the back substitution, it will be very clear. Okay, it will be very clear 1 0 0 0 1 0 0 0 1 multiplied with that ABC, the column matrix, solution matrix ABC. So it is very clear that C equal to 0 and B equal to 0 and A equal to 0. That is the idea. Okay, so one more problem we can try, maybe, but we have only 5 minutes. But I'll do that problem next class. So we'll do that concepts also. The subspace spanned by the vectors. Okay, so we'll do one problem for that also. We have discussed the linear independent, dependent, and then we have also discussed the basis. Okay, and then basis and how the basis vectors, how the standard basis vector should be expressed as linear combination of those vectors. And you can see some books and do some more problems. Okay, of course, if you follow different books, then different approaches might have used, because some people use the matrix approach, some people may not use go for matrix, and some people use it using the definitions and all. They will try to do that. So you follow any books, that's not an issue. So next class we will discuss one or two problems related to your subspaces which are spanned by the vectors alpha 1, alpha 2, alpha 3, whatever vector you consider. Whatever vectors you consider, so we can try that. And once we finish the subspace spanned by some vectors, suppose we give one or two problems in that, then we'll